And we are back working on attaching this electric smart car motor to that transmission from a 1956 Jeep CJ5. Last time I made the adapter plate. Today we're going to work on the input shaft. I need to make the input shaft fit the spline on the motor. It's close. This is a Bosch SMG 180-120. It's a kind of off-the-shelf motor that was used in a bunch of electric vehicles. Luckily, Bosch's marketing material specifies what this spline is. It's a DIN 5480-N 26 by 1.25 by 18 by 9H. It's been a while looking at the DIN 5480 standard, and what I found out was the N means NABA, which is a hub or internal spline. That one's obvious. 26 is the reference diameter. 1.25 is the module, basically the size of the tooth. 18 is the spline count. I was able to source a 1.25 module, 18 tooth, 30 degrees involute spline cutter straight from China, so at least I've got that taken care of. And 9H is the tolerance or fitness class. This one basically means we're going for sort of a line-on-line, very tight tolerance on it. But this one, I'm just going to read this one. DIN 5480 was structured to permit easy slip fitting of components, such as, for instance, ball or roller bearings. This condition is met by making the reference diameter equal to the bore of the bearing and then modifying the profiles of the teeth of the hub and shaft accordingly. Reference diameter is not the major or minor diameter of the spline. Really? On top of that, this is wrong. This is 25. If you look up a DIN 5480 spline chart for an 18-tooth 1.25 module spline, it's a reference diameter of 25 millimeters. So we're going to do what we always do, which is take some measurements, make a test piece, see how it fits, and adjust accordingly. Came up with a major diameter of 25.25 millimeters. For clearance, we'll call that 25 millimeters. That gives us 984 thousandths, because all my tools are in inches. Deal with it. Minor diameter, 22.68, 892 thousandths. We want a little bit of clearance on that, so let's call it 900. Tooth depth of 42. Seems like a good answer. You know, it happens to me more than I care to admit that I take a roughing pass or even just an initial pass and hit the dimension exactly. It's better to be lucky than good. I've got my dividing head all set up, clocked in vertically and side to side. Set up for 18 divisions. It'll be 2 turns and 6 holes on a 27-hole plate. I'm going to come down, touch off my cutter, then move halfway down and start cutting splines. At the end of the last video I did on this project, I answered a few questions that I knew would come up, and some people ask them anyway. Maybe if I do it at the beginning this time, people won't wander off before they learn something. The most common one seems to be, why are you putting a transmission in an electric vehicle? EVs don't have transmissions. The reality is most production's EVs have a single-speed gearbox, a gear reduction usually between 8 and 10 to 1. I need a gear reduction, and it turns out I have one in the form of a transmission that's made to mate up with the rest of the drivetrain in this vehicle. This is a pretty well-proven way of doing an EV conversion. People have been doing this for a long time. I also plan on using this Jeep in a variety of terrain, so having the option of different gearing will be a positive. The other one that comes up a lot is, how will you shift without a clutch? Most likely I'll just leave it in second most of the time. But because the rotating mass of the motor is so low, it should be possible to shift without the clutch anyway. I'll just need to give the synchros time to work, and maybe add a switch to turn off regeneration. Sort of a virtual clutch. Well, I made a mistake and didn't land back where I was supposed to. I'm going to go ahead and take this to final depth, just because it's a test piece. We'll see how it comes out. I'm going to keep this in the chuck for test fitting it and just pull the whole chuck off. That way if I want to come back and cut them deeper, I don't lose my indexing. Well, half of that looks really nice, but it is not even close to fitting. Right, and this clearance needs to go the other way. I am also not on center. I guess I'm just having trouble with math and counting today. That's why we make test pieces. Went a few more rounds with that. Finally got it to fit in there. That's definitely not right though, so I made another one. And that one's not right either. So I made a third one, and that one is pretty darn close. So I made a fourth one, and that one fits really tight. So I think I've got numbers that I can work with and move on to the real shaft. I am going for an outer diameter of 980 thousandths. The problem I run into is the input shaft for a Borg-Warner T90A is 937 thousandths. But there's a solution to that, which is to use the input shaft from a T90J, which is 1.125", and the business end is the same on it. To maximize concentricity on this, I'd like to turn this between centers. I've got a center hole in this end, but there's not really one in this end, and this surface is a needle bearing race. So, what was the other thing I wanted to rant about? Oh yeah, Lovejoy couplings. That's going to come up. It seems that if you have a vague idea of the existence of Lovejoy couplings, you feel the need to suggest them for any and all sorts of power transmission. Lovejoy couplings are great for dealing with misalignment low torque applications, and they may even make them as an option for higher torque applications. But I haven't really looked into that because the people who do EV conversions say they cause more problems than they solve. They're also not used in commercial EVs. Instead, I'm going to take the approach to just try to maximize the concentricity in my machining. Oh, and I screwed up the press fit on this and had to make the part twice. I don't have a drive dog that's going to work for this on the lathe, so I'm going to use the set screw, and obviously I really don't want this coming out while I'm turning it, so we're going to use a little red thread locker on there. I also don't want it to push against that center, so just go in by hand. Do a quick check to see how that's running. Alright, I gotta come clean. I wasn't going to mention this, but last night I was playing around with trying to turn part of this, just pressure turning it between centers without the little dog pin in there, just to see how this cuts. And I spun this enough that now the center hole is kind of buggered up, so got the steady rest out, and I'm just going to rebore that center hole. It occurred to me that since this setup is going to be more rigid, and there's a lot of the shaft I don't need, it makes sense to get rid of some of it now. This is also a good way to test to see how well this metal is going to cut. So, those experiments reveal basically what I've been worrying about for the past several months, which is this part of the shaft is hard, and this part of the shaft is really hard. This section I can actually turn with carbide, and actually this is all that I really need of this. This spline section I could actually take some off with this brazed carbide tool, but it was dulling at every pass. I tried a piece of high-speed steel on this section, and it didn't work. It dulled the tool and just kind of chewed it up a little bit, which means even if I do turn this down to the diameter I need with carbide, I won't be able to cut my splines in it. So, I guess it's time to anneal this. In one of my Patreon updates, I was talking about this problem, and one of my supporters there suggested using one of these little induction heaters. Now, I shouldn't really have to say, do as I say, not as I do. This is not really the right way to set this up. I should have it in a nice enclosure and all that, but I'm still trying to figure this out. In reading up on these, one of the things that comes up a lot is they like to burn out, and that's because there's really nothing on the heater that controls the amperage, so you need to monitor it. So I have a little voltage and amperage monitor here. I've also just got a 5-gallon bucket with a submersible pump for cooling the coil. We'll see how this goes. Got out the thermal camera. Okay. Keeping an eye on the MOSFETs on the circuit board there, and also keeping an eye on the shaft. This might be asking a little too much of that little induction heater, but it definitely did something. Made it pretty colors. Let's see if we got the desired result. The interrupted cut on the spline section was still really hard on the carbide tool, but I could cut it pretty well with high-speed steel. Well, I tried to anneal a little bit more of this with a smaller coil, and pretty much immediately burned up this MOSFET. We'll replace that at some point. Obviously, I don't understand how this works quite well enough yet, but what I do understand is the appeal of the induction heater is being able to closely control where the heat is applied. I don't want to anneal the part of this with the gears on it, but I can achieve that with a torch by keeping them submerged in a bucket of water. I know sometimes when I change my approach mid-project, it might seem like I don't know what I'm doing or I'm making it up as I go, but the reality is that these are all things that I've thought through well in advance, and now I'm just kind of working through the list. I've got this to a point where I'm pretty confident I'll be able to cut those splines in it, and now I'm going to completely change my approach to this. If you're working through something like this and you haven't done it before, you need to be willing to adjust and adapt and go to plan B, C, or D as you go. There's a lot of that here. I wasn't happy how it was running on this center hole. I tried my best before, so I stuck this in the 4-jaw chuck, got it dialed in off that surface, and the best I could off this surface as well. I flipped this thing around, clocked it in again, tried to face it off, and then realized I really just don't have a good press fit on that. I really didn't want to Loctite this in, but I think it's going to be the best bet. It's been a while trying different positions to try to get any run out in the setup to cancel out with any run out in the part, and I think I've got it about as good as I can get it. Since I got all of my mistakes out of the way on my test pieces, this time I'm doing a scratch pass first to make sure I've got my indexing right, and provide a visual confirmation on subsequent passes that I'm in the right spot. When I made the test pieces, I zeroed this dial. I haven't touched it since, so that should be on dimension. Looking at that, I think it needs to go a little bit deeper, but I think it's time for a test fit. And just as predicted, it does not fit yet. It occurred to me I should do this the proper way and measure it over some pins. In this case, they're 1/8 inch end mills. Test piece is 1141. That one is 179. In theory, this setup should be repeatable, but given how things are going, I'm going to be a little careful with this first cut. And because I annealed this, I now need to harden it. So back to the same bucket of water setup. The big problem here is I don't know what alloy this is, so I'm guessing at the process to get to a result that's also a bit of a guess. My first attempt I quenched in oil, but I wasn't happy with that, so for the second one I tried a water quench. That seemed to work better. Going after this with my hardness tester files. I've got to admit these files are something I struggle with. I just do not have the feel for them. I never know. It's probably, yeah, it's hard. I'm going to temper it for a little bit. I tempered this thing at 400 degrees for a couple of hours because that seemed like a good temperature. And while it was hot, I used the opportunity to drive out the piece of aluminum using the threads I'd tapped in it earlier. So, did I harden that enough? Did I harden it too much? Did I temper it too much? I don't really know. It's not as hard as the original one. It seems like it's probably harder than the hub and the motor. I got some pretty good advice from Chirpy to take some of the scrap, make some sample pieces, heat treat them the same way, smack them with a hammer and see what happens. This one's been hardened, but not tempered at all. It's exactly what I would expect to happen. And one that's been tempered about like the shaft. That obviously has a big stress riser where it's going to break. Let's try beating on this piece. So I think the thing to do is to put this all together and try to get this Jeep running, and it's either going to be fine or it's not, in which case I'll have learned something from it and I can go back and make a better one. I think I'm going to skip over most of the generic T90 reassembly because there are other better videos about that, and well, it would basically be you watching me watch that video. So I'll bring you back when I have this all together. This is one of those things that, even though I know what's going to happen, no matter how many times I do this, it never gets old. This is a permanent magnet motor. Let's go first gear. Ha! Never gets old. The other good news here is everything feels like it's running smoothly and not binding up at all. Went ahead, got the transfer case added on, all buttoned up. I'm real happy with how this is looking, and it's pretty much ready to go in the Jeep. So I think that's a good spot to leave off for this one. As always, thank you for watching, and if you want to see me put this in the Jeep, stick around.